Voyager One has been flying for 47 years without stopping, and it has covered 0.002% of 1 light-year. 1 light-year, that single distance, is the reason humanity may never reach another star. Today, we find out exactly how impossible that journey really is, and why the universe built a perfect trap that no engine, no fuel, and no amount of human will can simply overpower. Now let's begin. In 1977, a spacecraft left Earth. Not toward the Moon, not toward Mars. It launched with a mission more ambitious than anything humanity had ever attempted before. Fly straight out into the darkness and never stop. 47 years have passed. Voyager 1 is still flying. Not a single second of rest, not a single pause, just a continuous straight line into the void between stars. And as of today, it holds a record that no other human-made object has ever come close to breaking. It is the most distant spacecraft in the entire history of our civilization. So how far has it actually gone? 47 years of uninterrupted flight. And it has covered exactly 0.002% of 1 light-year, not 2%. Not 0.2%. 0.002%. Sit with that number for a moment. The human brain was simply not built to feel the true difference between 0.2 and 0.002. Those two numbers look similar on a page, but the gap between them is enormous. So instead of numbers, try a picture. Imagine 1 light-year stretched out as the length of a standard football field, 100 meters from one end zone to the other. Voyager 1, after 47 years of flying without a single break, has traveled exactly 2 centimeters across that field. Not a full stride, not even the length of your index finger from knuckle to tip. Now, here is the critical thing to understand. This is not a failure of engineering. Voyager 1 is a genuine marvel. It is still functioning after nearly half a century in space. It is still sending data home. It reached interstellar space, the region beyond the sun's influence, and it is still out there measuring things no instrument had ever measured before. Nothing went wrong with that spacecraft. The problem is not the machine. The problem is the distance itself. 1 light-year equals 9,461,000,000,000 kilometers. That figure shows up in every astronomy textbook ever printed. But reading a number and truly grasping it are two very different things. 9 trillion kilometers means almost nothing to a brain designed to navigate a world measured in meters and kilometers. So think about it differently. Take every kilometer that every human being has ever traveled across all of recorded history. Every walk taken, every road driven, every ocean crossed by ship, every flight made by airplane from the first footsteps of ancient civilizations, all the way to this morning. Add every single one of those journeys together into one grand total. That combined distance still does not reach 1% of 1 light-year. Think about that. Every journey ever made by our entire species combined is less than 1% of the distance we are talking about. Or try a scale model. Shrink the sun down to the size of a tennis ball. At that scale, Earth sits about 8 meters away from it, a reasonable distance. You could walk it in a few seconds. But at that same scale, 1 light-year is 550 kilometers away from that tennis ball. Not 550 meters, 550 kilometers. That is roughly the distance from New York to Detroit, reduced down from the actual size of the universe. Or think about light itself. Light travels at approximately 299,000 kilometers per second, the fastest speed anything in the universe can move. Sunlight moving at that speed takes 8 minutes to reach Earth after leaving the surface of the Sunday. It takes 17 hours to reach the outer boundary of our solar system. And it takes 4 years and 25 days to reach Proxima Centauri, the nearest star to our Sunday. 4 years and 25 days for light. For the fastest spacecraft humanity has ever launched, that same journey takes 6,600 years. 6,600 years. When the crew members of that hypothetical ship stepped aboard, humanity was still living in the Bronze Age. The first writing systems had just been invented. The Great Pyramids of Egypt had not yet been constructed. The Roman Empire would not rise for another 3,000 years. And by the time that ship finally arrived at Proxima Centauri, we have absolutely no idea what human civilization would look like, or whether it would exist at all. And that is just the nearest star. Not one full light year away, just 4.24 light years. Humanity lives inside an extraordinarily small bubble, surrounded by an incomprehensible vastness. And that bubble has invisible walls that no engine currently in existence and no engine currently on the drawing board can come close to breaking through. Here is one more way to feel the weight of this. If Voyager One experienced a critical failure right now and needed rescue, it would take 22 hours just for a rescue signal to reach its location. 22 hours only to transmit a message, then another 22 hours for any response to come back. Have you ever stopped to consider that rescue in deep space is nearly a meaningless concept? But here is where things get even more striking. Parker Solar Probe, the fastest spacecraft humanity has ever built, travels 15 times faster than Voyager One. 15 times faster. And even at that speed, it would still require 1,560 years to cross one single light year. So, where does the real limit actually lie? And why do physicists describe it as a wall that no amount of energy can ever break? This is the question almost everyone asks the moment they hear those numbers. Why not build a bigger engine? Why not pour in more fuel? Make everything more powerful and just fly faster? It sounds like the obvious solution. It sounds like the kind of problem that money and engineering should eventually be able to solve. But here is the thing. That question, as reasonable as it sounds, runs directly into one of the most ruthless mathematical traps in all of physics. A trap so thorough and so unforgiving that humanity walked straight into it on the very first rocket launch and has been wrestling with it ever since. The trap has a name. It is called the Tsiolkovsky rocket equation. The idea behind it is not complicated. In fact, it can be explained in a single chain of logic. To make a spacecraft go faster, you need fuel. Fuel has mass. To move that mass through space, you need more fuel. But that additional fuel also has mass. Moving that extra mass requires even more fuel. And that fuel has mass too. The loop continues, and it never closes in your favor. Every time you try to go a little faster, the amount of fuel required does not grow gradually. It grows exponentially. Each step forward costs dramatically more than the step before it. The Saturn V rocket that sent the Apollo astronauts to the moon is the most powerful demonstration of this trap ever constructed. At the moment of launch, Saturn V weighed 2,800 tons. Of that total, the actual spacecraft, the capsule carrying the crew, along with all their equipment and supplies, weighed roughly 5 tons. Everything else, the remaining 2,795 tons, was fuel. Fuel to push the rocket upward. Fuel to push the remaining fuel. Fuel stacked on top of fuel, stacked on top of more fuel, all of it burning away just to deliver 5 tons to the moon and back. And the moon is only about 1/374th of one light year from Earth. Now scale that up. Imagine trying to reach 10% of the speed of light using chemical propulsion, the same basic technology behind every rocket ever launched. To push just 1 kilogram of actual payload to that velocity would require energy equivalent to roughly 10,000 tons of gasoline. Not to move a spacecraft, to move 1 kilogram. For a real crewed mission with everything needed for survival, the ratio of fuel to payload would reach into the thousands. In purely physical terms, you would need a structure larger than the moon just to accelerate a single car to 10% of the speed of light through chemistry alone. 10% of the speed of light still puts Proxima Centauri more than 40 years away. That is the first wall. But the second wall is harsher, and it comes from a direction almost nobody expects. At everyday speeds, physics is predictable. Double your velocity, you need 4 times the energy. Triple it 9 times. The math is clean and straightforward. But as you push toward the speed of light, that clean math falls apart completely. At 50% of the speed of light, the energy required is not simply 5 times what it takes at 10%, it is nearly 30 times more. The relationship between speed and energy becomes non-linear in a way that punishes every additional gain far more than the one before it. At 90% of the speed of light, The effective mass of the spacecraft, the mass that physics sees and must account for, rises to 2.3 times its original value. The physical structure of the ship has not changed, but to push it any faster requires energy as though it weighs 2.3 times more than it actually does, which means you need more energy to move the energy you just added. At 99% of the speed of light, that multiplier climbs to 7 times the original mass. At 99.9%, it reaches 22 times. And at exactly 100% at the speed of light itself, the effective mass becomes infinite. The energy required to reach that speed is not merely very large. It is not extreme or astronomical. It is infinite in the strict mathematical sense of the word. No finite source of energy anywhere in the universe can push any object with mass all the way to the speed of light. This is not an engineering limitation waiting to be solved. This is how reality is constructed. And if the rocket equation and relativistic mass were not already enough, there is one more problem that rarely gets the attention it deserves. The space between stars is not a perfect vacuum. Scattered through that vast darkness are dust particles, atoms of gas, microscopic fragments of matter drifting silently in all directions. At ordinary speeds, they are completely harmless. A spacecraft passes through without noticing them. But at 80% of the speed of light, a single particle the size of a grain of rice hitting the hull releases energy equivalent to a heavy artillery shell. Over decades of continuous travel, those collisions accumulate. Speed does not only demand enormous energy, it demands that you solve several different impossibilities at the same time. The universe does not need walls. It does not need guards or warning signs. It only needs physics, which never arrives late, never takes a day off, never accepts any negotiation, and has no sense of humor whatsoever. Even with unlimited resources and unlimited determination, you simply cannot just fly faster, knowing that what does it actually say about where humanity stands in this universe. But the history of science is filled with moments where people found a path not by driving straight through a wall, but by discovering a way around it, entirely. And there have been real projects backed by real money, pursued by real scientists, aimed at finding exactly those paths. One of them was so extreme that the United States government was forced to shut it down, not because it failed, but because it worked far too well. In 1958, a group of American scientists sat down and proposed the following plan with complete seriousness. Build a spacecraft, attach a massive steel plate to the back of it, then continuously detonate nuclear bombs behind that plate and ride the shockwaves into space. This was not science fiction. This was not a thought experiment scribbled on a napkin. This was a fully funded government research program with some of the most brilliant physicists of the 20th century working on it full-time. The project had a name, a budget, an engineering team, and detailed technical blueprints. It was called Project Orion, and nobody laughed at them. Because they were right. The physics behind the idea is straightforward enough to follow without any equations. Each nuclear detonation releases an enormous pulse of energy. That pulse slams into the thick steel plate attached to the rear of the spacecraft. The plate transfers that force into a set of heavy-duty shock absorbers, and the shock absorbers push the ship forward. Then, another bomb detonates. Then, another. Over and over, hundreds of times per minute, each explosion giving the spacecraft another push, building velocity steadily through the vacuum of space. Think of it as riding a controlled nuclear fireworks display, except the fireworks are atomic bombs, and the ride leads to the stars. The theoretical top speed achievable with this method was between 3 and 5% of the speed of light. With more advanced designs incorporating larger bombs and optimized geometry, some calculations pushed that estimate toward 10%. At 5% of the speed of light, a spacecraft could reach Proxima Centauri in roughly 85 years. That is within a single human lifetime. A person who boarded that ship at the age of 25 could potentially live to see another star system with their own eyes. One of the scientists working directly on Project Orion was Freeman Dyson, widely regarded as one of the most original and rigorous physicists of the entire 20th century. Dyson reviewed the engineering, checked the calculations, and concluded that the concept was physically sound. not theoretically interesting, not worth exploring further. Physically sound meaning it could actually be built, and it would actually work. The largest version ever designed on paper would have weighed 8 million tons at launch and carried 300,000 nuclear bombs on board. It was large enough, in Dyson's own words, to carry an entire city into space. So why does nobody know about Project Orion? Why is it not in history books alongside the Apollo program? It was not cancelled because the physics failed. It was cancelled because of politics. The Partial Nuclear Test Ban Treaty of 1963 prohibited the detonation of nuclear devices outside of the atmosphere. 4 years later, the Outer Space Treaty of 1967 banned nuclear weapons in space entirely. Project Orion was not technically a weapon, but it relied on nuclear detonations, and the treaties made any further development legally impossible. The program was shut down, the blueprints were filed away, and one of the most audacious engineering proposals in human history quietly disappeared. Freeman Dyson reflected on this outcome years later. He described it as the death of the greatest space dream that was ever designed with genuine seriousness. Not the greatest dream ever imagined, the greatest one that was ever actually engineered. Project Orion stopped not because humanity lacked the capability, but because humanity lacked the political permission. In 1973, a different group took a different approach. The British Interplanetary Society spent 5 years designing an unmanned interstellar probe that would use nuclear fusion rather than nuclear bombs. They called it Project Daedalus. The design they produced was enormous. The total launch mass came to 54,000 tons. Of that, 50,000 tons was fuel. The actual scientific payload, the instruments that would do the real work of exploration, weighed 450 tons. That gives a fuel-to-payload ratio of 111:1, a number that illustrates more vividly than almost anything else just how punishing the rocket equation truly is. Over 100 tons of fuel burned for every single ton of useful cargo delivered. Despite that brutal ratio, Daedalus was designed to reach 12% of the speed of light. At that velocity, the journey to Barnard's star, located 5.9 light-years from Earth, would take approximately 50 years. People who watched the launch could realistically expect to live long enough to receive the first data transmissions from another star system. The fuel of choice was helium-3, an isotope that undergoes fusion reactions far more efficiently than ordinary hydrogen. There is one significant problem with helium-3. It barely exists on Earth. The quantities needed for a mission of this scale would have to be harvested from the upper atmosphere of Jupiter, using technology that does not currently exist and has never been seriously prototyped. The conclusion reached after 5 years of detailed engineering work was clear and honest. Project Daedalus was physically valid. No law of nature prevented it from working. It simply required solving 4 or 5 separate technological problems, each of which would qualify as a civilization-level engineering achievement on its own. Project Orion was stopped by politics. Project Daedalus was stopped by the gap between what physics permits and what engineering can currently deliver. Project Orion was cancelled because of a political treaty, not because the physics failed. If those treaties had never existed, where do you think humanity would be in interstellar travel by the year 2025? Orion and Daedalus both represented what happens when you take existing physics and push it in directions nobody had considered before. Both were real, both were serious, and both ran into walls that had nothing to do with the laws of nature. But there is a project happening right now today with real funding and real researchers at real universities built around a design that turns every traditional assumption about spacecraft completely upside down. And the entire spacecraft fits on your fingernail. Every spacecraft ever launched in the history of human spaceflight was built around the same unspoken assumption. The ship must be large enough to carry its own fuel. That assumption shaped every design decision made over the past century. It drove the creation of massive rocket stages, enormous fuel tanks, and complex propulsion systems that dominated the weight and cost of every mission ever flown. Nobody seriously questioned it, because it seemed like the only option available. Breakthrough Starshot throws that assumption out entirely. In April of 2016, Russian billionaire Yuri Milner stood at a press conference in New York and announced an investment of $100 million into a program designed to send a spacecraft to another star within a 26 generation. Standing beside him was Stephen Hawking, the most recognizable physicist alive at the time, lending the project his explicit support. The spacecraft they described carried no fuel at all. It did not need any, because the energy source would stay on Earth. The design centers on a chip, roughly the size and weight of a postage stamp, weighing approximately 1 gram. Attached to this chip is a sail, a thin, reflective sheet, several meters across, made from a material roughly 1,000 times thinner than a soap bubble. This entire assembly chip plus sail is the spacecraft. To launch it, a ground-based array of lasers producing a combined output of 100 gigawatts focuses its beam onto the sail. 100 gigawatts is comparable to the entire electricity output of the United Kingdom at any given moment. That concentrated beam of light pushes against the sail through radiation pressure. The same gentle force that solar sails rely on, but amplified to an almost incomprehensible degree. Within a few minutes of continuous acceleration, the 1-gram spacecraft reaches 20% of the speed of light. That translates to approximately 216 million kilometers per hour. At 20% of the speed of light, the journey to Alpha Centauri, 4.37 light-years away, takes 20 years. The data transmitted back from the Alpha Centauri system travels at the speed of light and takes 4 years to arrive at Earth. Total time from launch to receiving the first images, 24 years. For the first time in the history of interstellar mission design, the people who press the launch button could reasonably expect to be alive when the results come back. That single fact separates Breakthrough Starshot from every previous concept discussed in this story. The reason this is possible at all comes back to the trap described in the previous section. The rocket equation punishes mass. The more your spacecraft weighs, the more fuel you need, and the more fuel you carry, the more your spacecraft weighs. Breakthrough Starshot escapes this trap completely by making the spacecraft so small that the equation becomes irrelevant. A 1-gram payload does not need tons of propellant. It needs a very powerful beam of light and a very good mirror. But the engineering challenges are real and significant, and they deserve to be stated plainly rather than glossed over. 100 gigawatts of laser power is a staggering figure. Building an array capable of producing and focusing that much energy onto a target smaller than a coin, a target that is simultaneously accelerating away from the beam at increasing speed, represents a technological challenge beyond anything currently demonstrated. The pointing accuracy required is extraordinary. The sail itself must reflect 99.999% of the laser energy that strikes it. If it absorbs even a fraction more than that, at 100 gigawatt input power, the heat generated would be enough to destroy the spacecraft in seconds. The materials science required to achieve that level of reflectivity across the entire surface of the sail does not yet exist at the scale needed. Then there is the question of survival during the voyage itself. At 20% of the speed of light, even a particle the size of a large molecule carries significant energy upon impact. Over 20 years of travel through interstellar space, the accumulated damage from dust and gas particles is a problem that current models can estimate but not fully solve. And when the spacecraft arrives at Alpha Centauri, it cannot stop. There is no mechanism for deceleration. The chip will pass through the Alpha Centauri system at 20% of the speed of light, capturing images and measurements for a window of perhaps a few minutes, then disappear permanently into the darkness beyond. It will never return. There is no retrieval, no second pass, no second chance. But none of these are reasons to dismiss the project. They are engineering problems, not violations of physical law. The difference matters enormously. Everything about Project Orion and Project Daedalus that made them impossible was also an engineering problem rather than a physical one. The question is whether the engineering can be solved within a time frame that makes the mission meaningful. Breakthrough Starshot is the first interstellar mission concept in history where the answer to that question might genuinely be yes, within the lifetimes of people already alive. If Breakthrough Starshot succeeds and sends a chip the size of your fingernail to Alpha Centauri in 20 years, but that chip flies straight through without stopping, Would you consider that a success or a different kind of failure? Starshot solves the speed problem for an object with almost no mass at all. But what about a human being? 70 kilograms of biology, requiring oxygen, water, food, stable temperature, psychological coherence, and social connection across decades of deep space travel. That is where the physics steps aside and a harder problem takes over entirely. There is a fact about the physical world that once you truly understand it, changes the way you think about time permanently. Not as a metaphor, not as philosophy, as something that has been measured directly, repeatedly, and confirmed beyond any reasonable doubt. Time does not pass at the same rate for everyone. This is not a feeling. It is not a matter of perception or psychological experience. It is a measurable physical reality. Two identical clocks, perfectly synchronized, placed in different conditions, will tick at different rates and accumulate different amounts of elapsed time. When you bring them back together and compare them, the difference is real. The clocks genuinely disagree about how much time has passed. Neither one is wrong. They both measured time correctly. Time itself passed differently for each of them. This has been tested hundreds of times using atomic clocks, the most precise timekeeping instruments ever built. The results are always consistent, always in exact agreement with the predictions made by Einstein's special theory of relativity over a century ago. You have actually been relying on this effect today without knowing it. The GPS system in your phone works by receiving signals from satellites orbiting Earth at an altitude of roughly 20,000 kilometers. Those satellites are moving at about 14,000 kilometers per hour relative to the ground. Because of that speed, time passes slightly slower for the clocks aboard those satellites compared to clocks on Earth's surface. The difference is small, only a few microseconds per day. But if the system did not correct for it constantly, the position errors would accumulate at a rate of roughly 10 kilometers per day. Your navigation app would become useless within hours. Every time you follow a route on your phone, you are benefiting from a correction applied to account for the fact that time genuinely passes at different speeds depending on how fast you are moving. At the speeds of ordinary life, the effect is tiny. But as velocity increases toward the speed of light, the effect grows into something that reshapes the entire meaning of a long journey. At 90% of the speed of light, 10 years passing outside the spacecraft translates to 4.4 years experienced by the crew on board. The people inside age 4.4 years, while a decade passes for everyone they left behind. At 99% of the speed of light, that same 10 years outside shrinks to 1.4 years on board. The crew ages less than a year and a half, while the rest of the universe moves through an entire decade. At 99.9%, 10 years outside becomes 5.4 months on board. Less than half a year of personal experience for every decade of time passing in the outside world. Now carry that logic to its practical conclusion. A spacecraft traveling at 99.9% of the speed of light toward a star, 100 light-years away, would take just over 100 years to arrive as measured from Earth. But the crew on board would experience that journey as approximately 1.4 years. They would step off the ship having aged barely more than a year, while 100 years had passed at home. The return trip takes another 1.4 years for the crew, another 100 years for Earth. The total round trip from the crew's perspective, roughly 3 years of personal experience. From Earth's perspective, over 2 centuries. Everyone the crew knew when they left would be long dead before they returned. The world they came home to would have changed beyond recognition. Their children, if they had any, would have lived out full lives and died while the crew was still in transit. The crew would arrive home as strangers in a civilization that had moved on without them, in a world that barely remembered their departure. This is not a hypothetical scenario invented to make the physics feel dramatic. It is the direct mathematical consequence of how velocity affects time, and it has already been observed at very small scales in the real world. Military pilots who fly fast jets throughout a 20-year career accumulate a measurable time difference compared to people who spent those same years on the ground. The gap amounts to only a few millionths of a second over a full career, negligible in practical terms. But it is real, it is measured, and it is confirmed. At the speeds available to current aircraft, the effect barely registers. at the speeds required for interstellar travel, the same effect becomes the defining feature of the entire journey. And unlike the distance problem or the energy problem, this one cannot be engineered away. It is not a challenge waiting for a better material or a more efficient engine. It is baked into the structure of time itself. The faster you travel, the more severely your personal clock diverges from the clocks of everyone you left behind. There is no workaround. There is no shielding against it. It simply happens as reliably and indifferently as gravity. This is the part of interstellar travel that rarely gets the weight it deserves in popular discussions of the subject. Most conversations focus on the energy required, the fuel needed, the engines that do not exist yet. Those are real problems, and they are enormous. But even in the most optimistic scenario, even in a future where all of those engineering problems have been solved, even if a crew can cross dozens of light years, in a few years of personal experience, the time dilation problem waits at the end of the journey with a reality that no amount of place, technology can soften. You can leave, you can travel, you can arrive, but you cannot truly come home, not to the home you left. The universe does not prevent the journey. It simply ensures that the return is in the deepest sense impossible. The voyage to a star, 50 light-years away in 3 years of personal experience, would mean returning to a trident that had aged 100 years without you. Every person you knew would be gone. Every relationship, every connection, every piece of the life you left behind would have dissolved into history while you were away. You would land on your home planet as a visitor from a past that everyone else had already moved beyond. Is that a journey worth taking? If you could reach a star 50 light-years away in 3 years of personal experience, but when you returned, 100 years would have passed on Earth and no one you ever knew would still be alive, would you go? Physics has now laid out its full case. Distance that defies every engine ever built. Energy requirements that approach infinity as speed increases. And time itself that bends and fractures under the weight of velocity, ensuring that even a successful journey becomes a one-way door. 3 separate walls, each one complete on its own, all of them stacked on top of each other. But humanity has never had a good record of accepting walls. And in the next act, the most ambitious ideas ever seriously proposed take the stage from the most energetic fuel the universe permits to the theoretical possibility of bending space itself. Some of them are genuine physics. Some of them wear the costume of science while hiding something far less certain underneath. The honest question is, which is which? Picture the year 2200. A vessel the size of a small city sits in orbit above Earth, its hull stretching for kilometers. Its interior divided into living quarters, farms, hospitals, schools, and power plants. 10,000 people are on board. They have said goodbye to everyone they love. They know with absolute certainty that they will never see another planet. They will be born, live out their entire lives, grow old, and die inside this ship. Their children will do the same, and their children's children. And the 30 generations that follow, they know all of this, and they are choosing to go anyway. This is not a mass suicide. This is arguably the most courageous decision any group of human beings could ever make, to sacrifice the entirety of one's own existence so that descendants 30 generations removed might one day set foot on a world orbiting another star. People who will never be met. People who might not even remember who made the sacrifice that put them there. The generation ship is humanity's oldest serious answer to the problem of interstellar distance. Accept that we are slow. Accept that the journey is long. Then build something that carries not just people but an entire self-sustaining civilization capable of surviving the crossing. The idea sounds straightforward until you begin working through the details. Then it becomes one of the most complex engineering and social challenges ever seriously considered. Start with biology. 10,000 people sounds like a substantial population. In the context of preserving genetic health across 1,000 years, it is uncomfortably small. Population genetics research suggests that maintaining genuine genetic diversity across 30 or more generations requires a minimum founding population of somewhere between 10,000 and 40,000 individuals, depending on reproduction patterns, random genetic drift, and the accumulation of harmful mutations over time. In isolated populations on Earth, the effects of reduced genetic diversity are well documented. Island communities cut off from outside contact for multiple generations show increased rates of hereditary disease, reduced immune function, and the gradual accumulation of genetic problems that larger, more connected populations dilute. Naturally, the same pressures would apply to any crew confined to a spacecraft for 1,000 years, with no possibility of genetic exchange with the outside world. Then there is the life support problem. The International Space Station recycles water and filters air continuously. It is an impressive engineering achievement. It also requires resupply missions every few months, without which it could not sustain its crew for more than a limited time. No closed-loop life support system ever tested in any experimental setting has maintained complete self-sufficiency for more than 2 to 3 years. A generation ship would need to sustain its ecosystem not for 2 years, but for 1,000, with no possibility of resupply from outside, and no margin for failure in the core systems that keep people alive. But the biological challenges, serious as they are, may not be the hardest part. The hardest part might be keeping the mission alive across generations who had no say in joining it. The first generation understands. They volunteered. They know why the journey matters. They feel the weight of the mission personally, and they carry it with genuine conviction. By the third generation, Earth is a story told by grandparents. Something heard about but never seen. No open sky, no horizon stretching to the distance, no seasons, no rain, no wind. The ship is the only world these people have ever known, and the destination is a concept rather than a place. By the 10th generation, 300 years have passed since departure. The founders are not just dead, they are ancient history. Who guarantees that the people alive at that point still feel bound by promises made by ancestors they know only through records and legend? History is full of institutions, traditions, and obligations that seemed permanent and then quietly dissolved across enough generations. By the 20th generation, the ship's population may have developed its own religious frameworks, its own linguistic evolution, its own moral hierarchies, its own understanding of purpose and meaning. The original mission plan, drawn up by engineers on Earth 1,000 years earlier, could by then be regarded as myth, as scripture, or as an irrelevant relic of a civilization that no longer feels like home. And then there is the question that almost nobody asks until it is framed directly. When the 30th generation finally arrives at the destination star, after 1,000 years of travel, will they actually want to leave the ship? The ship is their entire world. It is all they have ever known, all their parents ever knew, all their grandparents ever knew, reaching back through 30 generations. A planet is an abstraction. Open sky, unfiltered air, exposed, ground weather, unpredictability, the absence of controlled walls. These would be genuinely alien experiences to people who have spent their entire civilization inside a sealed vessel. The very thing the mission was designed to deliver might feel to the people asked to receive it like the most frightening thing imaginable. There is also the question of knowledge, preservation, and history gives us no comfort here. Ancient Rome developed a concrete formula capable of surviving, submerged in seawater for thousands of years without degrading. That formula was lost after the empire collapsed. Historians and materials scientists only recovered the key details in the 21st century, nearly 1,500 years after the knowledge disappeared. The Antikythera mechanism, a mechanical astronomical computer built in ancient Greece, was so sophisticated that no equivalent device appeared again for more than 1,400 years. The engineering knowledge required to build it simply vanished. On a ship traveling for 1,000 years, a single generation that fails to properly transmit the technical knowledge needed to maintain the nuclear reactor does not just lose an interesting historical skill. Everyone on board dies in the cold dark between stars. So to state the problem plainly, the hardest challenge facing a generation ship is not the engine, not the food supply, not the radiation shielding. It is this: how do you make Generation 15 people who have never seen Earth and will never see the destination care enough about arriving to keep the mission alive? That is, in essence, the most difficult personnel management problem in the history of civilization, with the consequence of failure being that everyone dies in interstellar space. If you were given the choice, would you rather be among the first generation to board a ship like that knowing you would die on it, or would you stay on Earth and watch it leave? The generation ship is the solution built on acceptance. Accept the slowness. Accept the distance. Accept that you personally will pay the price while someone else centuries later receives the reward. But there is another direction entirely, one that refuses to accept any of those terms. It reaches instead for the most energetically dense fuel that physics allows to exist, something so powerful that 1 kilogram of it carries energy equivalent to everything a large nation consumes in electricity across an entire year, and it tries to simply tear through the distance with pure speed. The universe appears to have a sense of irony. It created a fuel so theoretically perfect that nothing could ever surpass it. A fuel where 100% of the mass is converted directly into energy, where the efficiency ceiling set by physics itself is reached completely, where no reaction of any kind could extract more power from a given amount of decided material. Then it made that fuel almost impossible to produce, completely impossible to store using conventional means, and extraordinarily difficult to use safely, even in the most optimistic engineering scenarios. That fuel is antimatter. And this is its actual story. Every particle of ordinary matter has a corresponding antiparticle with the same mass but opposite charge. The antiparticle of an electron is a positron. The antiparticle of a proton is an antiproton. When a particle meets its antiparticle, both are annihilated instantly and completely converting the entire combined mass into energy. Not most of the mass, not a large fraction of it, all of it. This is the process described by Einstein's equation, relating mass and energy. 1 kilogram of antimatter meeting 1 kilogram of ordinary matter releases approximately 1.8 times 10 to the power of 17 joules of energy. To put that figure in context, burning 2 kilograms of gasoline releases roughly 66 million joules. Antimatter annihilation of the same total mass releases approximately 2.7 billion times more energy than that combustion. 2.7 billion times more energy from the same amount of mass. With a theoretically perfect antimatter drive, a spacecraft could accelerate to between 70 and 80% of the speed of light. At that velocity, 1 light-year takes between 15 and 17 months to cross. The journey to Proxima Centauri, 4.24 light-years away, would take approximately 6 years. Not 6,000 years. Not 600 years. 6 years. That is the promise. Now for the reality. CERN, the European Organization for Nuclear Research, operates the largest and most powerful particle accelerator complex on Earth. Among its many capabilities, it can produce antiprotons and positrons and combine them into antihydrogen atoms. The total amount of antimatter CERN produces in a year is somewhere between 1 and 10 nanograms. A nanogram is 1/1,000,000th of a gram. To accumulate just 1 gram of antimatter at current production rates would require somewhere between 100 million and 1 billion years of continuous operation at CERN. That range comfortably exceeds the remaining lifespan of the Sunday. The estimated cost of producing 1 gram of antimatter using current technology runs into figures that exceed the combined gross domestic product of every nation on Earth multiplied many times over. Antimatter is not expensive in the way that rare metals or exotic materials are expensive. It is expensive in a category so far beyond ordinary economic thinking that the comparison barely makes sense. Storage presents a separate problem of equal severity. Antimatter annihilates on contact with any ordinary matter whatsoever, including air molecules. It cannot touch the walls of any container. The only way to hold it is suspended in a perfect vacuum using powerful magnetic fields that keep the antiparticles away from all physical surfaces. Any interruption of electrical power to those magnetic fields, even for a single second, results in immediate annihilation of whatever is stored. On a spacecraft traveling between stars for years or decades, maintaining uninterrupted power to the containment system without a single failure becomes a constraint of extraordinary difficulty. And even if production and storage were somehow solved, there is still the problem of actually converting the annihilation energy into forward thrust. When matter and antimatter annihilate, the energy is released primarily as high-energy gamma rays and neutrinos. Gamma rays are extraordinarily penetrating radiation that passes through most materials without interacting. Neutrinos interact with ordinary matter so rarely that they pass through the entire Earth almost without effect. Channeling either of these into useful directed thrust is a profound engineering challenge. Current estimates suggest that a realistic antimatter drive might convert somewhere between 30 and 40% of the annihilation energy into actual propulsion, with the rest radiating away uselessly in all directions. Then, there is the radiation shielding required to protect the crew from the gamma rays produced continuously by the engine. That shielding must be thick and heavy. Heavy shielding increases the mass of the spacecraft. Increased mass requires more fuel to accelerate. More fuel means more mass. The same merciless loop encountered in every other propulsion discussion appears here again, even with the most energetically perfect fuel the universe permits. Antimatter is, in the most literal sense, the theoretical ceiling of what physics allows for a conventional propulsion system. No fuel could ever be more energy-dense. No reaction could ever be more complete. And yet the gap between that ceiling and anything humanity can currently build or even seriously plan toward is so vast that it makes the gap between chemical rockets and interstellar travel look modest by comparison. If humanity committed every resource available to it for 200 years to solving the antimatter production problem, setting aside all competing priorities for 2 full centuries, would that be the right choice? Antimatter represents the absolute upper boundary of what current physics permits, inside the rules as they exist. But some physicists are not interested in playing within those rules. They want to change the rules entirely. And they have found, at least on paper, a way to move faster than light without technically violating relativity at all. The question worth asking honestly is whether what they found is real physics or mathematics dressed up to look like it. There is an important distinction that rarely gets made clearly enough in conversations about faster-than-light travel. There is a difference between violating physics and requiring physics we do not yet know. Breaking the speed of light by accelerating through space falls into the first category. That is genuinely impossible, according to everything we understand about reality. But there is a second category, ideas that do not break any known law but depend on ingredients that may or may not exist in nature. Warp drive belongs to the second category, and that single distinction is simultaneously the reason for genuine excitement and the reason for serious caution. In 1994, a Mexican physicist named Miguel Alcubierre was working through the mathematics of Einstein's field equations, the same equations that describe how mass and energy curve spacetime and produce the effects we call gravity. He found a solution to those equations that described something remarkable. A region of spacetime shaped like a bubble with a spacecraft sitting stationary inside it. Behind the bubble, space expands. In front of the bubble, space contracts. The bubble itself moves through the universe. The ship inside does not move relative to the space immediately surrounding it. It simply sits there while the bubble carries it forward the way a surfer rides a wave without swimming through the water. The elegance of this idea is that it does not require anything inside the bubble to travel faster than light through space. The ship is stationary relative to its local space-time environment. What moves faster than light is the bubble itself, and space has no speed limit. There is no rule in physics that prevents space from expanding or contracting at any rate. The early universe demonstrated this directly during the period cosmologists call cosmic inflation, when space expanded at a rate far exceeding the speed of light. That expansion is accepted physics, confirmed by multiple independent lines of evidence. So Alcubierre found a mathematical solution to Einstein's equations that describes a structure capable of moving a spacecraft across interstellar distances at superluminal effective speeds without placing anything inside the bubble. In violation of special relativity, the mathematics is valid. The equations are correct. This is not pseudoscience. It was published in a peer-reviewed journal and has been taken seriously by physicists ever since. Now for the honest assessment of why it almost certainly cannot be built. To create the Alcubierre bubble, you need a specific type of material. Physicists call it exotic matter, and its defining property is negative energy density. Ordinary matter has positive energy density. Every substance ever observed, every material ever measured, every particle ever detected has positive energy density. Negative energy density has never been observed at any macroscopic scale in nature. There is one quantum mechanical effect that produces a tiny amount of negative energy. It is called the Casimir effect, and it occurs in the microscopic gap between two closely spaced conducting plates in a vacuum, where quantum fluctuations create a measurable attractive force. The effect is real and has been confirmed experimentally, but the amount of negative energy involved is extraordinarily small. Calculations suggest that the quantity of exotic matter needed to sustain an Alcubierre bubble large enough to contain a spacecraft would exceed the amount produced by the Casimir effect by a factor of approximately 10 to the power of Pani, 32. That is not 32 times more. It is a 1 followed by 32 zeros. The gap between what the Casimir effect provides and what a warp drive requires is larger than the gap between a single atom and the observable universe. Beyond the exotic matter problem, there is a control problem with no obvious solution. The front of a moving Alcubierre bubble is by definition moving faster than light. Information inside the bubble cannot reach the front of the bubble faster than the bubble itself is moving. This means that anyone inside the ship has no way to send a signal to the leading edge of their own bubble. There is no mechanism by which the crew could steer slow down or make any adjustments to the bubble once it is in motion. You would have to set your destination before activating the drive and then simply hope the trajectory was calculated correctly. There is also a radiation problem. As the bubble moves through space, particles and radiation accumulate at the leading edge. When the bubble is eventually deactivated and the ship arrives at its destination, that accumulated energy is released in a concentrated burst. Depending on the journey, length and conditions along the route, that burst could be energetic enough to destroy everything at the destination point. A ship arriving at Alpha Centauri via warp drive might effectively detonate upon arrival. The honest conclusion is this: the Alcubierre drive is a mathematically valid solution to a correct physical equation. It describes a real structure within the framework of general relativity. But building it requires exotic matter with negative energy density at scales that may simply not be achievable in the physical universe we actually inhabit. It is not impossible in the way that exceeding the speed of light by brute force is impossible, but it requires ingredients that may not exist. Wormholes present a similar situation. The mathematics of general relativity permits structures that connect two distant points in spacetime through a shortcut, a tunnel through the geometry of the universe, rather than a path across its surface. Einstein and physicist Nathan Rosen first described this possibility in 1935, which is why such structures are sometimes called Einstein-Rosen bridges. The mathematics is entirely valid. No one disputes that. But a traversable wormhole, one large enough and stable enough for a spacecraft to pass through, requires the same exotic matter with negative energy density needed to sustain the Alcubierre bubble. Without it, any naturally forming wormhole would collapse instantly upon the attempt to use it. And there is a practical problem that rarely gets stated clearly. To create a wormhole shortcut between Earth and Alpha Centauri, you need to get one end of the wormhole to Alpha Centauri first. That means traveling there by conventional means to deliver the far end of the tunnel. The journey takes 6,600 years. Only after completing that conventional trip does the shortcut become available. Wormholes might eventually be useful for maintaining fast connections between colonies that were established through long conventional journeys. They do not solve the problem of getting there in the first place. Warp drive and wormholes are both valid in the mathematics, but both require exotic matter that may not exist at the necessary scales in nature. Is that a reason to keep investigating, or a signal to focus on more grounded approaches? Warp drive and wormholes may represent the future of interstellar travel, or they may turn out to be mathematical structures with no physical counterpart in our universe. While that question remains open, the universe has already been quietly revealing something far more concrete. Thousands of actual worlds confirmed by observation, not theoretical, and some of them are keeping astronomers awake at night. Before 1992, humanity had a problem it rarely acknowledged openly. We did not actually know whether any other stars had planets. We assumed they did. The logic seemed sound. The sun had planets, other stars are similar to the sun, so presumably they have planets too. But assuming and knowing are entirely different things. For all of recorded history, every single planet ever confirmed by direct evidence orbited our own Sunday. Everything beyond was speculation. Then in 1992, astronomers detected the first confirmed planets orbiting another star, a pulsar designated PSRB 1257+12. 3 years later, in 1995, the first planet orbiting a Sun-like star was confirmed. It was named 51 Pegasi b, and it shattered assumptions about what planetary systems could look like by being a Jupiter-sized world orbiting its star in just 4 days. What followed was a transformation in our understanding of the universe. As of today, more than 5,700 exoplanets have been confirmed by multiple independent detection methods. Thousands more candidates await confirmation. The Kepler Space Telescope, which operated from 2009 to 2018, surveyed a small patch of sky and found planets around a significant fraction of the stars it observed. Statistical analysis of those results leads to a striking conclusion. On average, every star in the Milky Way hosts at least one planet. The Milky Way contains between 200 and 400 billion stars. That implies somewhere between 200 and 400 billion planets in our galaxy alone, before counting any of the estimated 2 trillion other galaxies in the observable universe. Planets are not rare. Planets are the default outcome of star formation. The question is no longer whether worlds exist around other stars. The question is what those worlds are like. Some of them are worth examining closely. The TRAPPIST-1 system, located 39 light-years from Earth, contains 7 rocky planets orbiting a small red dwarf star. All 7 are roughly Earth-sized. 3 of them sit within the habitable zone of their star, the range of orbital distances where liquid water could exist on a planetary surface under the right atmospheric conditions. The James Webb Space Telescope is currently analyzing the atmospheres of these planets. Results are ongoing, and the scientific community is watching carefully. Proxima Centauri b is the closest known exoplanet with any potential for habitability. It orbits Proxima Centauri, our nearest stellar neighbor, at a distance of 4.24 light-years. A planet that close is an extraordinary thing to know about, but its host star is a red dwarf prone to intense ultraviolet and X-ray flares, and Proxima Centauri b orbits close enough to its star that those flares could be severe. Whether complex life could survive that radiation environment is a genuinely open question. Then, there is K218b. This planet orbits a star 120 light-years from Earth. In 2023, the James Webb Space Telescope detected a spectral signal in its atmosphere, consistent with the presence of dimethyl sulfide. On Earth, dimethyl sulfide is produced exclusively by marine microorganisms. It is not known to arise from any purely geological or chemical process. The detection requires further confirmation, and the scientific community has been appropriately cautious about drawing conclusions. But it is the kind of result that does not allow comfortable indifference. Here is the question that rarely gets answered directly. If the dimethyl sulfide signal on K218b is confirmed as biological in origin, what actually changes a signal sent toward K218b travels for 120 years before arriving? Any response travels 120 years back. A single exchange of messages takes 240 years longer than the United States has existed as a nation. No one alive today would experience both sides of that conversation. With current technology, sending a physical probe to K218b would take incomprehensibly longer than any mission ever planned. But knowing that life exists somewhere else, knowing it with confirmed evidence rather than hopeful speculation, changes something that goes beyond technology and logistics. It changes the entire framework of the question. Life on Earth would no longer be an isolated accident, a single improbable spark in an otherwise barren cosmos. It would be evidence of a universe where life arises wherever conditions permit. It would suggest that the story of biology did not begin and end on one small planet, but is written across the galaxy in chemistry and time. That shift in understanding would be permanent and irreversible. You cannot unknow that the universe is alive, and yet we still could not reach it. Not with anything we currently have or anything currently in development. The distance remains exactly what it was before the discovery. The physics does not soften its constraints in response to what we learn. The gap between knowing something exists and being able to reach it might be the most quietly painful feature of our situation as a species. We can see across distances we cannot cross. We can detect chemistry we cannot touch. We can identify worlds we cannot visit. If tomorrow brought confirmed evidence of life on a planet 120 light-years away, knowing you could never receive a reply within your lifetime, would that make the universe feel less lonely or more? We know worlds are out. To there, we know why reaching them matters. But the largest question remaining is not whether we can make the journey eventually. It is what we are missing right now while we wait for the technology to catch up in a place far closer to home than any of those distant stars. That is where the final act begins, and it ends with something almost nobody expects. Everything discussed in the first two acts pointed outward. Toward Proxima Centauri, toward the TRAPPIST-1 system. Toward K218b, toward stars and worlds separated from us by distances that would take thousands of years to cross with anything we can currently build. The assumption running beneath all of it was that if life or habitable conditions exist anywhere beyond Earth, they must be out there somewhere, among those unreachable points of light. But what if the thing we have been searching for across light years has been sitting quietly inside our own solar system this entire time? Europa is one of Jupiter's 70-some moons. It orbits the largest planet in our solar system at a distance of roughly 628 million kilometers from Earth. That sounds remote until you compare it to anything discussed so far. Alpha Centauri is 4.24 light-years away. Europa is 67,000 times closer than that. In the context of interstellar distances, Europa is practically in the next room. Its surface looks from a distance like a cracked billiard ball, a pale sphere covered in a network of reddish-brown fractures running across a field of bright ice. That ice is between 15 and 25 kilometers thick. And beneath it, according to multiple lines of evidence, converging from different instruments and different missions, lies a global ocean of liquid saltwater. Not a small lake, not a subsurface pocket, a continuous ocean that wraps entirely around the moon beneath its frozen shell. Current estimates suggest this ocean contains roughly twice the volume of all Earth's oceans combined. More liquid water than exists anywhere else in the known solar system, sitting beneath the ice of a moon 400 million miles from the Sun. The strongest evidence for this ocean came from NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003. Galileo detected an induced magnetic field around Europa, a field that changes in response to Jupiter's powerful magnetosphere in a way that is most consistently explained by a layer of electrically conductive saltwater beneath the polar surface. This is not a theoretical prediction. It is a measured signal pointing to a specific conclusion, and the scientific consensus around it is strong. Now, here is why this matters more than a simple inventory of interesting moons. For most of the history of astrobiology, the search for life focused heavily on sunlight. Life on Earth is powered primarily by photosynthesis, which requires sunlight, which requires proximity to a star. Europa receives only a small fraction of the sunlight. Earth does. Its ocean sits beneath kilometers of ice, with essentially no light penetrating to the water below. By the traditional framework, it should be a dead and frozen world. But in the 1970s and 80s, oceanographers discovered something on Earth that reframed the entire question. At the bottom of Earth's oceans, in complete darkness along the mid-ocean ridges, where tectonic plates spread apart, there are hydrothermal vents. Superheated water, rich in dissolved minerals, pours out of the seafloor, and around those vents, in total darkness, supported by chemical energy rather than sunlight, entire ecosystems thrive. Tube worms meters-long dense colonies of shrimp, crabs, fish, microorganisms of extraordinary diversity, all living completely independently of the Sunday life on Earth, does not require sunlight. It requires liquid water, an energy source, and the right chemistry. Europa appears to have all three. Jupiter's gravitational field is so powerful that it continuously flexes and stretches Europa's interior as the Moon orbits. This tidal flexing generates heat inside the Moon, the same way repeatedly bending a metal rod makes it warm. That internal heat is sufficient to maintain geological activity, potentially including hydrothermal systems on the ocean floor, where warm, mineral-rich water meets the liquid ocean above. The conditions at the bottom of Europa's ocean may closely resemble the hydrothermal vent environments where some of Earth's most ancient life forms evolved. Water, energy, carbon chemistry. These are the three fundamental requirements for life as we understand it. Europa has reasonable evidence for all three. NASA launched the Europa Clipper mission in October of 2024. The spacecraft is currently en route to Jupiter and is expected to enter orbit around the giant planet in 2030. Once there, it will conduct approximately 49 close flybys of Europa, using a suite of instruments to map the surface, measure the thickness of the ice, analyze the composition of material on the surface, and search for signs of activity in the ice shell. It will not land, it will not drill through the ice, but it will provide the most detailed picture of Europa ever assembled, and what it finds will shape the next generation of missions. And then there is Enceladus. Saturn's sixth largest moon might be the most remarkable object in the solar system for astrobiology. It is small, roughly 500 kilometers across, and should by any reasonable expectation be a frozen geologically inert ball of ice. Instead, NASA's Cassini spacecraft discovered that Enceladus is venting a continuous plume of material from fractures near its south pole directly into space. That plume contains saltwater ice particles, molecular hydrogen silica nanoparticles, and complex organic molecules. Each of those components carries information. Molecular hydrogen, in this context, is particularly significant because it is produced on Earth when hot water reacts with certain types of rock in a process called serpentinization, which is associated with hydrothermal activity. Finding hydrogen in the plume of Enceladus is strong evidence that liquid water is interacting with hot rock somewhere beneath the surface. Cassini also detected phosphorus in material sampled from Enceladus. Phosphorus is one of the 6 elements considered essential to all known life. It forms the backbone of DNA and is central to adenosine triphosphate, the molecule that powers cellular processes in every living organism ever studied on Earth. Finding phosphorus in the plume of a moon, hundreds of millions of kilometers away, is a result that the scientific community did not fully anticipate. Here is the extraordinary practical implication. A spacecraft, flying through the plume of Enceladus, could collect samples of material that originated from the interior ocean of that moon, without needing to land, without needing to drill, without needing to melt through kilometers of possibles. Ice. The ocean is effectively offering its contents up for collection. Future missions could potentially analyze those samples for biosignatures directly. Humanity has spent decades designing faster engines and more ambitious propulsion systems to reach stars light years away. While an ocean moon, 1.5 billion kilometers from Earth, has been quietly spraying its interior contents into deep space available for collection by any spacecraft that happens to fly through. The universe apparently does have a sense of humor. We have been engineering our way toward Alpha Centauri, while Enceladus has essentially been waving at us from the backyard. If Europa Clipper in 2030 finds clear evidence of microbial life in the ocean beneath Europa's ice, how do you think that would change humanity's priorities in space exploration? The solar system is wider and stranger than 10. Almost anyone taught us to expect. But there is a deeper question waiting beneath everything discussed so far. One that even physicists argue about without resolution. Why are the distances between stars so large in the first place? Is that scale a random outcome, or is something more fundamental at work in the structure of the universe itself? We have spent a great deal of time establishing how large the distances are. We have not stopped to ask why. Why are stars separated by light years rather than light days? Why is the nearest stellar neighbor 4.24 light years away and not 4.24 million kilometers? Is the scale of the universe a coincidence, or does it reflect something deeper about the conditions that allow anything to exist at all? Modern physics has something to say about this, and the answer is simultaneously reassuring and deeply unsettling. The universe is governed by a set of fundamental constants. The gravitational constant determines how strongly masses attract each other. The fine structure constant governs the strength of electromagnetic interactions. The strong nuclear force holds atomic nuclei together. The cosmological constant describes the energy density of empty space and drives the expansion of the universe. These numbers are not derived from any deeper theory. They are measured values that simply are what they are, and the structure of everything that exists depends on them precisely. If the gravitational constant were slightly larger, gravity would be stronger throughout the universe. Stars would burn through their fuel faster, living far shorter lives. Planetary systems would form differently. The window of time available for complex chemistry and biology to develop before a star dies would shrink dramatically. If the gravitational constant were slightly smaller, stars might never ignite at all, and the universe would be a cold, dark place filled with diffuse gas that never condensed into anything. The margin for error is extraordinarily small. Calculations suggest that a change of roughly 1 part in a million in the gravitational constant would produce a universe structurally incompatible with the existence of stars, like our Sun, planets like Earth, or chemistry, complex enough for life. The same sensitivity applies across multiple fundamental constants. They are collectively tuned within extremely narrow ranges to permit a universe where matter can form, where stars can burn for billions of years, where planets can cool and stabilize, where chemistry can reach the complexity required for self-replication and eventually for consciousness. The large distances between stars are not arbitrary. They are a direct consequence of the density of matter in this universe, which is itself set by those fundamental constants. A universe with different constants might have stars much closer together or so far apart that no light ever crossed from one to another. The specific distances we find so overwhelming are a feature of the particular set of physical laws that happen to govern our universe. Laws fine-tuned enough to produce stars, planets, and the kind of beings who can sit and wonder about the distances between them. That is the anthropic principle stated in physical rather than philosophical terms. We exist in a universe whose constants permit our existence. The distances feel impossibly large from our perspective, because our perspective is that of creatures evolved to navigate a world measured in meters and kilometers. But those same distances are the inevitable consequence of the physics that allows us to exist at all. Now consider something that receives far less attention than it deserves. The universe is not only expanding but accelerating in its expansion. Distant galaxies are moving away from us faster over time, driven by the energy of empty space itself. This has a consequence that plays out over timescales so vast they are difficult to frame meaningfully. In approximately 150 billion years, most of the galaxies currently visible in our night sky will have receded beyond the cosmic horizon, the boundary beyond which the expansion of space carries objects away faster than pulse. Light can travel across the growing distance between us. Once a galaxy crosses that horizon, it is gone permanently. No signal it ever sends will reach us again. No observation we make will ever detect it. Civilizations that form 1 trillion years from now, if any exist, will inhabit a universe that looks completely different from ours. They will look out into space and see only their immediate galactic neighborhood. Everything else will have vanished beyond the horizon. They will have no way to know that billions of other galaxies once existed within observational range. They will have no access to the cosmic microwave background, the faint afterglow of the Big Bang that tells us so much about the origin and structure of the universe. The entire observable history that we use to build our cosmology will be invisible to them. We are living at an extraordinarily privileged moment. The universe is old enough that stars have formed, planets have cooled, and life has had time to develop and ask questions. But it is young enough that billions of galaxies remain observable, that the structure of the cosmos is still legible, that the evidence of how everything began is still within reach of our instruments. This window will not stay open forever. By cosmic standards, we arrived at a remarkable time. And yet the universe is almost entirely silent. The Milky Way is approximately 13 billion years old. That is enough time for civilizations far more technologically advanced than ours to have developed, expanded, and left detectable evidence across the galaxy many times over. If even a small fraction of the billions of planets in our galaxy produced intelligent life, and if even a small fraction of those civilizations developed the capability for interstellar travel or large-scale engineering, the signs of creating stealths, their presence should be detectable from Earth. They are not. No confirmed radio signals from another civilization, no megastructures altering the light curves of distant stars in ways that defy natural explanation. No artifacts, no signals, no unambiguous evidence of any kind that we are not the only technological civilization in the galaxy. This silence has a name, the Fermi paradox, after physicist Enrico Fermi, who asked the question simply and directly, where is everybody? 3 broad categories of answers exist. The distances between stars are so large and the speed of light so finite that signals and travelers simply have not had enough time to reach us yet, even from civilizations billions of years older. Alternatively, intelligent life capable of developing technology is extraordinarily rare, far rarer than the number of potentially habitable planets would suggest, and we may be genuinely alone or nearly so in the observable universe. Or the most uncomfortable possibility, something consistently ends civilizations before they reach the stage of spreading across stellar distances, a pattern that would apply to us as much as to any other species that has ever looked up at the night sky and wondered. Nobody knows which answer is correct. The silence continues. The question remains open. And it is in the honest assessment of many scientists who work on it, one of the most genuinely frightening, unresolved problems in all of science. Among the 3 explanations for cosmic silence, which one frightens you most if it turns out to be true? The universe is silent, but humanity is not. And the final question, after everything laid out across these 2 acts, is not whether we can eventually make the journey. It is what actually has value when we stand before a distance this vast. That is where this story ends, and it ends somewhere almost nobody expects. This whole journey began with numbers. 9,461,000,000,000 kilometers, 1,560 years, 0.002%. Those numbers appeared in the very first minutes of this story, and they have shaped everything that followed. The rocket equation, the relativistic mass barrier, the fuel ratios that demand structures larger than the moon, the generation ships that ask 30 generations of unborn people to carry a mission they never chose, the antimatter that costs more to produce than the entire economic output of every nation on Earth combined, the warp bubble that requires exotic matter no one has ever observed, the silence of a galaxy old enough to be filled with voices but somehow completely quiet. Every single one of those problems can be described with equations. Every constraint, every barrier, every seemingly impossible gap between where we are and where we want to go has a mathematical expression that captures it precisely. Physics is very good at measuring what stands between us and the stars. But there is one thing that does not appear in any of those equations. It is not in special relativity. It is not in the rocket equation. It is not in any model of propulsion, any calculation of stellar distance, any estimate of mission duration. It has no unit of measurement and no symbol in any formula ever written. It is the reason why, after everything laid out across these 3 acts, the question is still being asked. Consider what has actually happened, not in terms of spacecraft and propulsion systems, but in terms of reach. The Hubble Space Telescope and the James Webb Space Telescope have observed light that traveled for 13 billion years before entering their instruments. 13 billion light years. No physical object humanity has ever launched has traveled more than a tiny fraction of 1 light year from Earth. The farthest any human-made probe has gone is roughly 24 billion kilometers, which is approximately 0.00025 light-years. The telescopes we built are looking across distances roughly 52 trillion times greater than the farthest point any of our spacecraft have reached. We have not traveled 13 billion light-years, but we have seen that far. And seeing in this context is not a consolation prize. It is a genuine scientific achievement, measured in photons, collected spectra, analyzed distances, calculated, and conclusions drawn about the state of the universe less than 1 billion years after the Big Bang. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected a signal. That signal was a gravitational wave, a ripple in the fabric of space-time produced by two black holes colliding approximately 1.3 billion light-years away. The instrument that detected it measured a change in the distance between two mirrors caused by that passing wave. The change was smaller than 1,000th of the diameter of a proton. To detect a cosmic event 1.3 billion light-years away by measuring a distortion smaller than any subatomic structure we can directly observe, using lasers and mirrors and mathematics developed over decades, is not a modest achievement. It is one of the most precise measurements ever made by any civilization anywhere in history, as far as we know. Mathematics predicted the existence of black holes decades before any observation confirmed them. It predicted gravitational waves before any instrument was sensitive enough to detect them. It described the geometry of the Big Bang, the expansion of the universe, the existence of dark energy, and the precise pattern of temperature fluctuations in the cosmic microwave background, all before the observations arrived, to confirm the first's predictions. In each case, human reasoning traveled somewhere before human technology could follow. That is not a secondary achievement. That is not a footnote to the real story of space exploration. The capacity to build accurate, mathematical descriptions of physical reality and then confirm them through observation is the most powerful tool our species has ever developed. It has reached places no spacecraft will visit within any timescale we can currently imagine. So here is what can be stated honestly without false comfort and without unnecessary despair. Nobody knows when humanity will physically cross 1 light-year. It may be centuries from now. It may be longer. It may require physics that has not been discovered yet, engineering that cannot be currently conceived, and resources that no civilization has ever assembled. The timeline is genuinely unknown. Nobody knows whether warp drive will ever move from a valid mathematical solution to a buildable physical structure. The exotic matter problem may be permanently unsolvable within the laws of nature as they exist, or future physics may reveal a path that current understanding cannot see. That outcome is also genuinely unknown. Nobody knows with certainty whether life exists anywhere beyond Earth. Though the evidence accumulating around Europa, Enceladus, and exoplanet atmospheres makes the question feel less like speculation and more like an investigation with real leads. That answer is also unknown, but some things are known with certainty. Modern humans have existed for approximately 300,000 years. For most of that time, the accumulated knowledge of our species fit inside the memories of living people and was passed forward through spoken language and direct demonstration. Roughly 5,000 years ago, writing appeared and made it possible to store knowledge outside of individual minds. Roughly 500 years ago, the printing press made that stored knowledge widely accessible. And roughly 100 years ago, physics reached the point where it could describe the curvature of space-time, the energy locked inside matter, and the geometry of the cosmos from its first moments to its likely end. 300,000 years is approximately 1/46,000th of the time Voyager One would need to travel 1 full light-year at its current speed. In that vanishingly small fraction of a cosmic journey, a species that started with stone tools arrived at the ability to detect the collision of black holes 1.3 billion light-years away by measuring vibrations smaller than the positons, nucleus of an atom. The universe sets the distances, physics sets the constraints, humanity sets the questions, and across the entire history of this species, not one question seriously pursued has remained permanently unanswered. 1 light-year. 9 trillion, 461 billion kilometers. A distance large enough to confine the body, but not large enough to confine the question. After everything covered in this story, what is the one thing you most want humanity to figure out in the next 200 years?